Now earlier I mentioned the idea that if I had as an example f of x equals x squared, that this function does not have an inverse. Because the problem is if I have like a negative 2 here that's mapped to 4, then 2 is also mapped to 4. So if I put 4 inside the inverse function, it won't know which of these guys to go to. So that actually, I said, leads us to a way to figure out if a function has a inverse. Not all functions have inverses that are actually functions. And the way we're going to do that, or one method, is called the horizontal line test. Now you know about the vertical line test. We used the vertical line test way back in like pre-calculus or algebra to figure out if a function was in fact a function. The way we did that is we said, hey, if I draw a bunch of vertical lines, let me pick another color, that wasn't very good. If I draw a bunch of vertical lines, actually that color's not that bad, just a little bit light. Anyway, if I do a bunch of vertical lines here, then what happens is if I touch this graph at 2 places on any of these lines, 2 or more places, we say it's not a function. Well, that's exactly what we're going to do with the horizontal line test. Because of the horizontal line test, like if I come across here, I test a function in 2 places, which is obviously more than 1. So that means I have 2 values in my domain that go to the same value in the range. Hence, this would not have an inverse function. Now, if I had something that looks like this, here, obviously, if I draw a bunch of vertical lines, all is well. It's clearly a function. And likewise, if I draw a bunch of horizontal lines, clearly everywhere, or there's nowhere that my horizontal line would touch the graph in more than one place. So this would be, or this would qualify as a function that would in fact have an inverse. Now we can quantify this just a little bit further and say that, hey, an inverse, or for a function to have an inverse, that function must be 1, 2, 1. What that means is that in my domain, x1, x2, out to xn, and in my range, y1, y2, out to yk, when I put x1 into the function, it goes to some value y1, and y1's used up. It can never be used again. There are no other x's that will ever go to y1. That's what I mean by a one-to-one function. When I put x2 into here, it goes to y2. These other values of x will go in and come to other values of y. There are no y's that are shared. This is what we think of as a one-to-one function. So one-to-one functions do in fact have inverses. Now, a point of confusion, something we got to be careful of and kind of keep in mind, is if the point AB is on F. In other words, XY, AB, is on F. So here's an X. Here's a Y. So this point, XY, is on this on my function F. Then the inverse is going to have the function BA. So in other words, if you notice here, when I'm dealing with the range of my original function, that range becomes the domain of the inverse function. Hence, what was the range, these are values from the range, all the y values, now becomes the domain. So that means the point yx is on the inverse. So I put an x into function f, it gives me y. I put y into the inverse function, that y is now my domain, and that will give me the original value of x. Another way to say this is we could look at it like this: f of x equals y if and only if. Another way to write if and only if is with the double arrow. If and only if f inverse of y is equal to x. So here's my AB, and then here's my BA. Now, like I said a moment ago, that a function has an inverse if and only if the function is in fact one-to-one. Now, another way to determine one-to-one relationship is if f is strictly monotonic on its entire domain. So if I have a function that is strictly monotonic on its entire domain, then I can say, hey, this thing is in fact one-to-one. So how do we determine if it's monotonic? Something that monotonic is something it's consistent. So something that's monotonic increasing is always increasing. Something that's monotonic decreasing is always decreasing. And how can we do that? Well, we can check with a derivative. The basic idea, if I have f of x, and then from that I find the derivative ddx of f of x, if ddx of f of x is greater than 0 for all x on the domain, and it may be a restricted domain. I may not be going from negative infinity to infinity. I may be interested in only a small piece of it. Then, if that's true, then f is monotonic. Specifically, f is monotonic decreasing. If ddx of f of x is less than 0, in other words, negative, for all x on that domain, then f is also monotonic. This is monotonic increasing, this is monotonic decreasing. So by checking what's happening with the first derivative, we can determine where the function is monotonic, which in turn helps us figure out if it's going to have an inverse. And just very briefly here, a quick graph. Something that perhaps looks like this. This would have a first derivative that's positive everywhere because I'm constantly increasing. A function that perhaps looks like this. This would have a first derivative that is negative because the tangent lines, the slopes of the tangent line, are going to be negative everywhere.